Assalamu alaikum warahmatullah. Welcome everybody. Today we have Flowmeter experiment in fluid mechanics lab. Principles. So Flowmeter is just a device, and this device is used to measure the volumetric flow rate or mass flow rate of gas or liquid, so any fluid in the pipe. So now you want to measure the amount of flow in this system, so you can connect it to a flow meter. This flow meter is based on the pressure drop. Calculate the pressure drop. So once you calculate the pressure drop, so you can determine the amount of flow in the pipe. And this pressure drop is due to the change in the velocity of the fluid. So it creates like for example, if you have a pipe and this pipe have a specific velocity, and once you make like a hole or for example decrease the area, so the velocity will increase. When velocity increase, so the pressure drop will decrease, and according to the pressure drop, so you can determine the amount of velocity. So accordingly you can determine the flow rate if you know the cross-sectional area. So we have different types of flow meters, but the most common one in industry is Venturi and Orifice. So as you can see, this is the Venturi type. This is the cross-sectional. So we create like smaller cross section between 2 points. So here, as you can see, so this is smaller one, so there will be a difference in the velocity, and accordingly it will be pressure drop as well. So for principles, now as you know, this is Bernoulli equation. So we have P1 over rho g plus kinetic head v squared 1 over 2g plus z1 static head plus or potential head plus equal p2 over rho g for the second point plus v squared 2 over 2g plus z2. Since 2 points are on the same height or same level, so we can cancel z1 and z2. Then p1 over rho g plus kinetic v1 squared over 2g equal p2 over rho g plus v squared 2 over 2g. As you can see here, we ignored the head loss. Okay, we ignored. That means we assume the flow here is ideal. Okay, so the flow is ideal. I assumed my flow is ideal. Okay, now from the continuity, as you know, mass flow rate 1 equal mass flow rate 2. Okay, and when the fluid is have a constant, almost incompressible, or can't be its constant density, so we can remove the density. As you know, rho q1 equal rho q2. Okay, so rho will be cancelled, and q equals a times v, cross-sectional area times velocity, so a1 v1 equal a2 v2. Okay, now the idea is how can I calculate v2, okay, from here. So let's standardize the equation. So now, as you know, we know v1. Okay, we want to cancel v1. Okay, just to keep the v2. So v1 equal a2 over a1 times v2, and as you know, a is by d squared over 4. So by d squared over by d squared, so they by and 4 will cancel each other. Now d refers to the smaller, and d capital refers to the wider or the bigger diameter. Okay, and let's say that d small over d capital equal beta. So I will use term beta. So then d squared small over d squared capital, so it equal to beta squared times v squared. Okay, so now let's replace or substitute this equation to the Bernoulli equation, this one. So now p1 over rho g times plus, so instead of v1 squared, I will use this one, beta powered 4 v squared 2 over 2g equal p2 over rho g plus v squared over 2g. Okay, now I will now I can exclude. So let's do some rearrangement. Okay, let's do some rearrangement. Okay, so P1 over rho g minus P2 over rho g equal V squared 2 over 2g minus beta squared V squared 2 over 2g. So I can take V squared 2 over as a common, okay, factor here. So 1 minus beta power 4, and here P1 minus P2 over rho g. Then I can find V squared 2 equal P1 minus P2 over rho g times 2g. Okay, so g and g will cancel each other over 1 minus beta power 4. So then finally I can get this is beta equal squared squared root of this value to beta 1 minus beta, so P1 minus P2 over rho 1 minus beta power 4. Okay, since Q, as we said, Q equal A1 V1 equal A2 V2. So since I already calculated V2 here, so times A, so I can find Q. So Q will be A times the root equation. So by this I can find the flow rate of the fluid in the pipe. Okay, so now P1 and P2, so we can measure it by manometer or by any pressure equipment, and beta powered 4 equal the D over D, so it will be the small diameter over bigger diameter. Okay, and of course rho is the density of the fluid inside the pipe. Okay, now if you remember, we assumed our equation based on ideal. Okay, but actually there's some head loss in the system. So due to the vortices and eddies and friction, so now since this is not ideal, okay, the actual is less than the ideal. So to compensate for this one, we added CD. So this is the ideal. Okay, this is this one equation without any pressure drop or any head loss. Okay, since the actual Q is less than the ideal one, so we should add a factor to compensate for the non-ideality in the system. It will be CD, and CD is known as discharge coefficient. Okay, so that means actual flow equals CD times ideal flow. So if the flow meter is ideal, that means the flow meter doesn't cause any loss in the head, so that means CD should be 1, okay, because actual will be ideal. But in case of the flow meter cause any head loss, as fraction and head loss increase, the CD should decrease to compensate for the difference between them. Okay, now how to calculate? Now we have the actual and we have ideal. So ideal is calculated from the equation. This is the ideal. Okay, this one is the ideal, and the actual one we calculated by any other way, like a stopwatch, volumetric bench, anything. So you can calculate and correlate the relation between them and find the slope. Slope will be the discharge coefficient. As you can see, it's almost 0.9. This is for Venturi. This is the experiment part. So as you can see here, we have like we have 3 points here. We can take these 2 points, okay, together, or these 2 points together. So, and as you know, the diameter here, okay, so you can calculate beta, and you can pressure drop between 2 points. They are connected together to the system. Orifice Flowmeter has exactly the same concept of Venturi, but only the difference in the shape. So the orifice has a hole, okay, hole inside, and when fluid goes, so it will cause a lot of friction loss, okay, and by this we can calculate the Q. So exactly the same, but as you can notice here, the discharge coefficient in Venturi is almost 0.9, while in Orifice is around 0.6. That means Orifice make more pressure drop than Venturi. Okay, so this one cause more head loss. Okay, that's because the sudden contraction here in Venturi, the contraction is not sudden because it's mostly, as you can see, like this. Okay, but here in Orifice it's sudden contraction. This sudden contraction leads to a lot of head loss. Okay, so this is the same concept. Now let's start for the experiment part. We can see the experiment part here.
Assalamu alaikum, welcome everybody. Today we have our experiment flow measurement apparatus. We have different settings are connecting together here. We have Venturi, we have Orifice and wide diffuser. And for every 2 points they are connected to manometers, so we can directly measure the pressure drop between any 2 points, and they are all shown on the manometer. We also have a rotometer as well. In this part, this is hydraulic bench, and it can show the actual flow rate digital, so liquid per second or liquid liter per second or liter per minute. So now we'll start our experiment. We have this valve. This valve is the inlet valve, and we have exit valve. Okay, so let's start our experiment. Okay. Now, the first step we always do, we have to exclude all air bubbles from the system. Now, so allow the water to circulate through the system. Okay, wait a little bit until now all of air has been accumulated. Air accumulated here in the top part. So now we can exclude, we want to exclude all the air from the system. So we can do it by a little bend of this apparatus. Okay. Now as you can see, all air accumulated here. So just here, okay, that's it. So now our system has no air bubbles inside the system. Now we can start our experiment. So the first part, we should allow some air to enter the system, to have like manometer like this. So to do this, first close the inlet valve. Okay, and keep the outlet valve open. Okay, so then vent valve. Now, I'm not sure if you can see by camera or not, but should all the height of all manometers should be the same. Okay, it's better to have the height to be around from 170 to 180. So I will allow more water. Now the system is ready to start. So now the open valve is closed. Okay, and as you can see, it's zero. The volumetric flow rate is 0 liter per second and liter per minute. So now let's start the experiment by opening the valve a little bit. Now as you can see, this is the actual volumetric flow rate. Okay. Now, for each 2 points, they are connected to manometer. So, for example, this is A and P as shown here. A and P, so this is Venturi, and these are the diameter, 25, 16. Okay, this is the Venturi throat, and this is the Venturi diameter. Okay, so this is important for calculation. Now, there are 2 points are connected to this manometer. So here, for example, is 240, and the other one is 230. 38. Okay, so this is the pressure drop between 2 points. So you should write down this pressure drop. As well, for the orifice, we should follow. So this is the orifice, 2 points are the orifice. So 240 and 228. As you can see, the orifice has more pressure drop than Venturi. Also, if you want to calculate the amount of flow rate in the wide diffuser, the summary, this is 2 points, so you can check the amount of pressure drop in the wide diffuser. Also here as well, this is rotometer. For the rotometer experiment, you should take the reading, the height, and check the actual and make the calibration curve between them. So you can check exactly when you check the amount of level height of the rotometer, you can know exactly the amount of actual flow rate. So now we can again increase the flow rate, okay, and take new readings or new heights, and then you can do it again, and by this you can conduct your experiment easily. So that's it about this experiment. Thank you so much. Assalamu alaikum.
Thank you everybody, hope you enjoyed the experiment, and see you again. Assalamu alaikum.